Ideally, if we were to put in a pulse of a liquid or something in order to test our flow reactors, ideally with a PFR, it would remain a nice even surge. Um, a pulse that would continue. However, as would be the real case, perhaps you may get where in your actual reactor you have a larger area, in which case you get more dispersion. Or in another case where you were to say it's simply too long to use a continuous pipe, if you were to say, okay, well, we'll just loop it back around. Well, we know that as soon as this were to go through the curve, you're going to get a lot more mixing than you would get in a simple pipe. And then similarly too with CSTR, we always idealize it that as soon as a pulse would go in, right away you would have instantly complete mixing, which would immediately fall off. But we realize that in reality, when our surge, when our pulse comes in, it's not going to be instantly mixed. It's going to take a little while to mix. Then you'll start getting it in all. And then finally it will start to decay. And of course, it'll make a difference if you have the drain on this side versus the drain on that side, how quickly you actually get up to what your highest concentration would be. So your profile may more easily be something like that, where that would drop off. And then similarly with your plug flow reactor, ideally you would have it where you would have just this pulse that would continue through. Whereas actually, if you start having elbows or if you have changes in size, anything that would break that up, you're now instead going to get more of a mix. So with this then, we take our data and we want to analyze the pulse data in order to figure out what the actual mixing conditions, the timing conditions, as everything goes through our reactor will be.
So the first thing I'd like to do with my data entered here in Excel is have a look at what my time profile looks like. So to do this, we'll go ahead and select our two rows. Let's do an insert and we'll do a display. Let's do it with the straight lines. So this gives us an idea of what our time profile looks like. So with this we can see it's somewhat similar. It's definitely not a plug flow reactor. It does look more similar to what we might expect from a CSTR. Okay, so let's get started now putting in our data for the rest of the table. The first step that we want to do is get the area under the curve. So with that, we want C delta T. So to do this, our first one's just going to be 0 because we have no time elapsed yet. Now here we can set up our first equation. This is going to be equal to our C times then the difference in the time that has elapsed, which in this case is just 1 second. Okay, so now we have this formula, which we can simply copy and paste down the rest of the column. And now, the next thing that we want to do is get a sum of these to get the area under the curve equals sum. Take our column and enter. So now this gives us our area under the curve, which now with this doesn't tell us a whole lot. This doesn't help us solve a whole lot until we're able to get this into a dimensionless form, because at this point we now have it in concentration over time, times time. So with this, then the next thing that we want to do to get rid of these dimensions is use our E equation. So with that, it's E equals, we now take C divided by, and let's make this look nice. Let's get our symbol, insert, close, and this is sum C, and then I have this in autocorrect since I use it enough, delta t. So now in this case, our formula that we'll be using for this column is simply we now take the c and we divide it by the sum. And now in this case we want to make sure that we reference this exact cell. So with that we press F4, which puts in the dollar signs, and that'll be a static reference. So now we can take this and we paste this in. And now our next step is we take the e function times, let's see, again do our delta time, and now we have, again, fairly simple equation. This is equal to E times, in this case, delta t is 0. So actually with this, just put in 0. Okay, now we have some elapsed time that we can use. In this case, it's going to be equal to our E times, again, we have the elapsed time, which is that minus the previous. Okay, we can take this and multiply it down through these columns. And now, if we did this right, we want to do a sum on this column. Copy and paste the sum. We should get 1. So now we've got it in a nice dimensionless, somewhat dimensionless form, giving us unity under our curve, so that now we can build our profile more from there. In the next step, we need our concentration for this. So in this case, subscript equals, and in this case we have the function minus k t. So now put in this formula, k, the exponent function, which we're now taking the negative k, and in this case we want the explicit, so hit F4 again, and then here it's times our time elapsed, and then we can copy this right down through. So this gives us the concentration that we would get with each of these elapsed times. So our next step now is to multiply the amount under the curve here as this elapse, what the time function comes out to be, in this case E. E times delta T times our concentration. Oops. Concentration, and we want subscript A. So we take our E delta T times our CA we copy this function and we paste it down through, and now we take the sum of this, and this now tells us how much of the of our concentration of Ca is left at the exit. So our actual amount that has converted, we can now take 1 minus, take 1 minus that. And so this is giving us an 88.4% conversion. And the next thing we want to do is get our mean time. What is the average time? So in looking at this, we want to know, when we look at all this area under the curve, what is our median? Where is the middle, where that we would have an equal area to the left and equal area to the right, so we can compare this yield to what it would be from CSTR or PFR. So with that, then we want to take our T times E. It's going to be delta T, and equals T times E delta T. And we'll copy this. Now, when we do the sum, boom. Simple as that. It gives us what the mean time for the reactants is in whatever structure we have here for our reactor. Now, comparing this time elapsed to what it would be, let me change this, better. Compare this to what our yield would be from, say, if we use, if we were able to use a regular plug flow reactor. This is instead going to give us the function equals exp minus k times time. So this would be for our PFR. And actually, how about we'll go ahead and put this down for what the actual conversion is. Let's change this to 1 minus. So PFR would give us a very high conversion versus CSTR, where in that case then we have our function would now become one minus 1 divided by 1. Got to remember to put our equal sign in. Okay, now we can get our reference times time. Okay, so now we're looking in this case at an 82% conversion for what an ideal CSTR would be, and in this case our actual reactor falls in between the two, which is what we can expect for this case.